Okay, so we are ready for today's session. Today's session would be on assignment 6, solving the previous year's assignment problems for assignment 6. And before we start, I would just put up all the links that are relevant for all of you. So that's the YouTube channel link. Then we have the Google Drive link where all the notes are uploaded. So that was YouTube channel where the videos are uploaded, and that's the Google Drive link where the notes are uploaded. So these are the two important links which you should save. So we will begin with today's session. So this week there wasn't any Python implementation lecture as such. So it was mostly a week wherein theory concepts were discussed, and so this assignment is also predominantly based on those theory concepts that have been discussed in the week. We do not have any Python questions as we have had in the previous few assignments. So this assignment is entirely theory based. So let us start solving this assignment. So we have the first question. Consider a basis B which is given as the basis of three vectors of the vector space R3. So if the vector space is R3, that's why the basis would have three elements. Then using the Gram-Schmidt process, an orthonormal basis for R3 corresponding to B is given by the set, and we need to select which of these options is an orthonormal basis obtained by Gram-Schmidt process from the given set B that we have. Now notice that we need to use the Gram-Schmidt process over here. The question states clearly that we need to use the Gram-Schmidt process, because if you see that option number C and option number D, these are also orthogonal vectors. In fact, option number C, this one is the standard basis for R3. This is the standard basis. It is indeed orthogonal and an orthonormal basis. But this is not the basis that we obtained from the Gram-Schmidt process from the given set of vectors. So even though this is the standard basis and it is orthonormal, this is not the correct answer. We need to find out an orthonormal basis starting from what is given to us by using the Gram-Schmidt process. Now, let me write down what the Gram-Schmidt process does. So we have the Gram-Schmidt process. So what we do is that we take the first vector as it is, and you can normalize it for an orthonormal basis. So this denominator is for normalizing. And so let this be x1, let this be x2, and this be x3. So the first basis vector that we obtain is from the first vector in the basis itself that we have. So that's the first vector. And for further vectors, like the nth vector that we will obtain would be as follows. Sorry, not x1, this is xn comma dot product with v1 in the direction of v1. Then you subtract the component of xn along v2, and so on. You keep subtracting up until n minus 1. So xn v n minus 1. in the direction of Vn minus 1. So this is the algorithm for Gram-Schmidt process. And then finally, you can normalize this vector by taking Vn and then normalizing it by its length. So normalization is to get orthonormal. So this Gram-Schmidt process gives you an orthogonal basis given from whatever basis that you have to start with. Now, even without solving this, even without applying this Gram-Schmidt process, I can directly tell you that the answer is option A. I do not even have to go through this process to be able to say that. And how can I do that? Like, how can I be so confident? That is because according to the Gram-Schmidt process, one of the vectors is in the same direction as the old basis vector. So you have an old basis vector, and then you will have the new basis vector formed by the Gram-Schmidt process. And one of these vectors from each of these sets would be exactly in the same direction, because that's how we start with the Gram-Schmidt process. We take our first vector to be exactly the same as one of the vectors of the old basis and then just normalize it. Now you can see that only option A has one vector which is in the same direction as the as the old basis, and that is like this basis vector is in the same direction as this x1. It has just been normalized by that scaling factor 1 over root 2, but other than that, it is exactly in the same direction. And there is no other option in this B, C, and D which have any vector which is in the same direction as one of the vectors in the old set B. But still, since the question says that we have to use the Gram-Schmidt process, and the aim is to demonstrate what the Gram-Schmidt process does, but even without that, we can answer this question. But nevertheless, let us apply the Gram-Schmidt process. So, according to the Gram-Schmidt process, V1 is the same as X1, just scaled. So that would be 1, 1, 0, and then scaled by the length, and that is root 2. That's that. And then V2 is X2 minus component of X2 along V1. That would be X2 is 1, 2, 0. That's my X2. Minus of the dot product. So the dot product would be 1 over root 2 times 0 plus 2 into 1 over root 2 plus 0 into 0 in the direction of V1. So that's 1 by 2 comma 0 minus 3 by 2, 1 comma 1 comma 0. So that's minus 1 by 2, 1 by 2 and 0. And then we can normalize it. So normalizing V2, normalizing it would be dividing V2 by its norm. So let's do that. And the norm of this would be 1 over root 2, because 1 by 4 plus 1 by 4, that's half, and square root of half, that's 1 over root 2. So this gives me the following. So that's my V2. And then V3, we can find out X3 minus component of X3 along V1 and minus component of X3 along V2. So 0, 1, 2 minus 0 into 1 over root 2. This is just the dot product, the standard dot product that we have. Just plain and simple algebra. So we can just simplify. And that is 0, 0, 2. And normalizing, so normalizing this is pretty much simple. V3 will be divided by its norm, and that is 2. So this is 0, 0, 1. So our orthonormal basis that we have formed is the set V1, V2, and V3, which is as follows: the normalized vectors. So that's the following. So this is you how to use the Gram-Schmidt ortho normalization process. And with this, you can basically obtain an orthogonal basis starting from a basis which need not be orthogonal. Coming over to the next question. Let W be the subspace of R4 spanned by the vectors. So we have two vectors which span a subspace of R4. Let the vector V be given as follows. We are given a vector V in R4 in the subspace. Sorry, not in the subspace, in the R4 space. Then which of the following vectors is in the subspace W and closest to the vector V? So we have a vector V which is not in the subspace W. It is in the vector space R4, and we need to find out a vector in the subspace W which is closest to the vector V. Now this is closely related to the Gram-Schmidt process that I wrote down. So let me copy this from here. So we will use this algorithm of Gram-Schmidt process for finding out the solution to this question. So again, we have the Gram-Schmidt process written down as follows. So let me just paste that algorithm. So this is the algorithm, and this can be rewritten as follows: as Vn is Xn minus some Pn. So we have this algorithm where Vn is Xn minus some component along V1 minus some component along V2 and so on and so forth. So this can be written as Xn minus Pn, where this Pn is the orthogonal projection of the vector xn on the subspace spanned by x1, x2 up until xn minus 1. And this Pn is the orthogonal projection. So by definition, that is the closest vector possible. So our closest vector would then be this Pn. So this closest vector is actually Pn, and we can find it out as follows. So it is V1, sorry, not V. So this is dot product of V that we are given with V1. So let this be V1 and let this be V2. So this is the thing. Let us put in the values. So that's the first term. Then the second term. So that's the thing. So simplifying this, so this Pn is essentially the closest vector. So Pn in the algorithm for Gram-Schmidt process is used as the closest vector. So this is option number B. Moving forward, consider the polar decomposition and singular value decomposition of a square matrix. So we are given as the polar decomposition. So this is polar and this is singular value decomposition. And then we need to find out the expression of V and P in terms of the matrices U, V, and S. So basically, we need to find out a relation between polar decomposition and singular value decomposition. So let us start. So singular value decomposition, sorry. So singular value decomposition is given as follows. A is equal to US V transpose. Over here, U and V are orthogonal matrices. Orthogonal meaning V transpose V is identity, similarly for U. And S is a diagonal matrix with elements being the singular values. So this we can introduce a V transpose V in between, because we know that V transpose V is equal to identity. So we have just introduced that over here. So this is U V transpose times VS V transpose. So now a product of orthogonal matrices are orthogonal. So that we have this, that product of orthogonal gives us orthogonal. So this U and V are orthogonal. So this UV transpose is also orthogonal. And this is symmetric. And it has non-negative eigenvalues. And this also comes from the similarity condition. So this VSV transpose, this is what this is the thing that we use for similarity transformation. And in a similarity transformation, the eigenvalues are preserved. So this is the similarity transform of the matrix S. Now S has elements as singular values on the diagonal, and those are the eigenvalues of the matrix as well, because S is a diagonal matrix, and in diagonal matrix the eigenvalues are nothing but the diagonal elements. Okay, before proceeding, I think there is someone who is asking some question in the chat box. So ma'am, can we say that Pn is the orthogonal projection on the subspace W? That's right, that's what we, so this is pertaining to the previous question. So that's what it is. So this Pn is the orthogonal projection onto that subspace W. So you are absolutely right. And since it is the orthogonal projection on that subspace W, it also, by definition of what we mean by closest, so it becomes the closest vector to the vector V. Because if you look like an intuitive 2D picture, if you want to see in R2, if I look at a 2D picture, and if I have a vector, if I have this vector in some direction, and I want to find out the something which is closest along the x direction. So what is that component? So how you would do that? You would just take the component along the x direction, and you would say that this is the best component that you can get along the x direction. So whenever you do take an orthogonal projection onto something, so that is like the closest you can achieve to that vector. If you take longer than this, well, you would not be close to this vector that we have over here. So if this is V and this is my x-axis, this is my y-axis, if I take longer component, let's say I take something up until here, then this will be very much far away from V if I find out if by definition of what is closest. So that's how it is defined. So yeah, coming back to this, so we know that S is a diagonal matrix with positive eigenvalues because singular values are positive. As a result of this, this VSV transpose, which is a similarity transformation, also has positive eigenvalues. I mean non-negative eigenvalues, because singular values are non-negative. So because in similarity transform, your eigenvalues are preserved. And this will then be written as some W times P, and this is what is known as the polar decomposition. So from here it is pretty much obvious that my W is UV transpose and my P is VSV transpose. So the correct option is option B. So now let us move ahead. Next question. Consider two matrices A and B of order 3 cross 4 and 4 cross 2 respectively. If C is equal to A times B, then which of the following statements is true? So this is about polar decomposition of non-square matrices. So in this case, we can have either right polar decomposition or left polar decomposition. Now let me write down. So what we have is A is 3 cross 4, B is 4 cross 2, and C is A times B. So this will have a dimension of 3 cross 2. Now by definition, my right polar decomposition would be for a matrix A which is M cross N, wherein M is greater than equal to N, and it will be given as the following, where U is basically an orthogonal, it has orthogonal columns. So it is M cross N with orthogonal columns. and P is n cross n positive semi-definite. Because it has non-negative eigenvalues. So this is my right polar decomposition. Now left polar would be as follows. So A is an m cross n matrix, but m this time is less than equal to n. So we will write it as follows, where H is an m cross n positive semi-definite, sorry, m cross m, not m cross n. M cross m positive semi-definite matrix, and U is an m cross n matrix with orthogonal columns. So from this definition, we can easily see that A will have left polar decomposition, because of for A, m is less than n. B will have right polar because m is greater than n. And C will also have right polar because again m is greater than n. That is 3 is greater than 2. So the correct option which matches is option D. A has left polar and B and C have right polar decomposition. So coming to the next question. So we have a matrix A given as follows, and the algebraic and we need to find out the algebraic and geometric multiplicity of the smallest eigenvalue of this matrix. So first we need to find out the eigenvalues and then we need to find out the eigenvectors. So let us start. So we have the eigenvalue equation. Ax equal to lambda x, and this we find the eigenvalues by taking the determinant of A minus lambda I as 0. So eigenvalues are found as follows. Determinant A minus lambda I is equal to 1 minus lambda, 0, 2, negative 1, 1 minus lambda, 3, 0, 0, 2 minus lambda. So this determinant, if you write down, is expanding along the first row. So that's it. So this is the equation, and this gives me that eigenvalues are 1, 1, 2. So that means the smallest eigenvalue is 1. Smallest eigenvalue is 1 and it has an algebraic multiplicity of 2. Why? Because it is the number of times it is being repeated. So 1 is being repeated 2 times and that's why its algebraic multiplicity is 2. Now we need to find out the eigenvectors that will give us the geometric multiplicity. So eigenvectors are found out as follows: A minus lambda I x equal to 0, and then sorry, not this, equal to 0. We can write this in the augmented matrix form. So A minus lambda I would be 0, 0, 2, negative 1, 0, 3, 0, 0, and 1. And this is the augmented matrix form, wherein we write down the matrix A minus lambda I and the column vector 0, the constant one, and then X is the one that we need to find out. So let us apply row operations. So first row operation, let us interchange R1 and R2. So this gives me the following. Next, let us make this leading coefficient 1. And then let R2 goes to not R2, R3. R3 goes to R3 minus half R2. So this would be 1, 0, negative 3, 0, 0, 2, and 0, 0, 0. And finally, let us say R2 goes to half R2. So we get this reduced row echelon form. So this is the reduced row echelon form. And our eigenvector x is written as, let's say, x, y, z. Then from this reduced row echelon form, what we get is the following equation. Two equations we get: x minus 3z equal to 0 and z equal to 0. So from this, we also get x equal to 0. Then we have only one free variable, which is y, and corresponding to this we would get the eigenvector x as 0, 1, 0, because there is only one free variable, that is y. So from this we obtain only one linearly independent eigenvector. And since we have only one linearly independent eigenvector, that means the geometric multiplicity is equal to 1. So algebraic multiplicity is 2, geometric multiplicity is 1. So option C. So algebraic multiplicity is the number of times the eigenvalue is repeated, and geometric multiplicity is the number of linearly independent eigenvectors that you can have corresponding to that eigenvalue. So next question is on minimal polynomials. So the minimal polynomial of the matrix A is, we need to find out what the minimal polynomial is. So before finding out the minimal polynomial, we need to know the characteristic polynomial. So characteristic polynomial. This is given by determinant of A minus lambda I, 2 minus lambda, so again, if we expand the determinant along the first row, we get 2 minus lambda cubed times 5 minus lambda. So, and setting this to 0 to get the eigenvalues. Then we can swap the sign, because this is equal to 0. So from this, what this is what we get as the characteristic polynomial. And since this is the characteristic polynomial, thus what we will have is the following. We would have, if instead of lambda, if we put a, and instead of 2, if we put 2 minus I, instead of 2 we need to put 2 times I, then what we get is the following, and this will also be equal to 0. So that is how from the characteristic polynomial we can get an expression in terms of A and the identity matrices. Then the minimal polynomial. What is minimal polynomial? So minimal polynomial is a polynomial which has degree less than or equal to the characteristic polynomial. So it has degree less than or equal to characteristic polynomial. So let us consider, so we need to reduce the degree, but notice that each term should occur at least one. That means we cannot get rid of a minus 5i because each of the eigenvalue coefficient needs to occur once. So if you think that in order to reduce the degree, we can get rid of a minus 5i and simply consider a minus 2i cubed, that is incorrect because each of the term needs to occur at least once. So in order to reduce the degree, we can consider a minus 2i squared times a minus 5i. So let us try and find this. A minus 2i squared times a minus 5i. This would be equal to a minus 2i. So this would be 0, 1, 0, 0. This is a minus 2i and this squared. That means another a minus 2i. Then times a minus 5i. So then we need to do simple multiplication. So let us multiply this. The first two matrices, let us do a minus 2i squared first. So this is 0, 0. First row is entirely 0. Second row will also be entirely 0 because it is a 0 row. Third row also 0. Then let us look at fourth row. So 0, 0. Then 1 into 3. And then 3 into 3, that is 9. Times a minus 5i. So this is this, and then let us multiply this. So what we get 0, 0, 0. Then second row is completely 0, so it will be 0. And then the fourth row, this column is 0. So fourth row, this first element 0, 0, 0, and again 0. So yeah, so this is nothing but the 0 matrix. So this can be a minimal polynomial. So this can be minimal polynomial because for minimal polynomial, we need that the expression equals 0 when we put in the matrix A, whatever matrix we have. But what if we further try and reduce the degree? So, because remember, minimal polynomial is a polynomial which has the least degree, wherein putting in A and the identity matrices, you get 0. So, we can still reduce the degree one more. So, let us consider reducing one more degree, a minus 2i times a minus 5i. So this would be 0, 1, 0, 0. This is a minus 2i and then a minus 5i. So let us do the multiplication. So you see that this is a non-zero matrix because we have a non-zero element present in this matrix over here. So this is the non-zero element. As a result, this matrix is not equal to a zero matrix. Therefore, we have a minus 2i whole squared, a minus 5i equal to 0, and this is the least degree that we can have. So this means that a minus 2i squared, a minus 5i is the minimal polynomial. And this would mean that is we have x minus 2 whole squared and x minus 5, because if you put instead of x the matrix A and instead of 2 the matrix 2 times I, then you get this. So this is the minimal polynomial that we have. So x minus 2 squared, x minus 5. So correct option is option C. So next question. The characteristic and minimal polynomials of a matrix A are given. So it is x minus 3 to the power 4, x minus 9 squared, and x minus 3 squared into x minus 9 squared. So this is the characteristic and minimal polynomials we are given. Then we need to find a possible JCF of the matrix. So JCF meaning what? It is Jordan canonical form. So you notice each of these matrices is a 6 cross 6 matrix, and the elements that I have not written are 0. So it would be too much tedious to write this thing. That's why I did not write. So all these blank spaces that are there, they are all 0, 0, 0. So I did not write it because writing would be all these zeros is pretty much cumbersome. So I only wrote down the non-zero elements for you, so you can fill in all these zeros over here. That is how you would fill in all the zeros. So all the elements that I've written in these options are the only non-zero elements in this. The rest of the elements in the 6 cross 6 matrix are supposed to be 0. So let us now figure out how to find out the Jordan canonical form. So in Jordan canonical form, so we have a matrix A, which is n cross n, and in Jordan canonical form we need to find out. So how do we find out? Well, eigenvalues are entries on main diagonal. So whatever the eigenvalues are, they will go on the main diagonal in the, sorry, not main eigenvalue, main diagonal in the Jordan canonical form. And then if your minimal polynomial MA lambda can be given as follows. So we have k eigenvalues, lambda 1, lambda 2 up until lambda k, and each Si in this is size of largest Jordan block corresponding to the eigenvalue lambda I. And then characteristic polynomial would be given as follows. Where each of these Ri is the number of occurrences of lambda I on main diagonal. So number of occurrences is essentially what is known as the algebraic multiplicity and then the geometric multiplicity of lambda I is the number of lambda I Jordan blocks. And then we have some properties of algebraic and geometric multiplicity. So algebraic multiplicity of lambda is the sum of sizes of Jordan blocks, and the geometric multiplicity of lambda I is the number of blocks corresponding to lambda. So let us use these properties to find out the Jordan canonical form. So we are given the characteristic polynomial as follows, and the minimal polynomial as follows. So from this, we can see that eigenvalues are lambda equal to 3 and lambda equal to 9. So 9 has an algebraic multiplicity of 2 and 3 has an algebraic multiplicity of 4. So let us say lambda 1 equal to 3. For this, our S1 is what? S1 is 2 and R1 is 4. And for lambda 2 equal to 9, we have S2 equal to 2 and R2 equal to 2. So this means that size of largest block is what? S2. So size of largest Jordan block is equal to S2, and that would be equal to 2. And then sum of sizes of Jordan blocks is equal to my basically the algebraic multiplicity of lambda, and that is my R2. So S2 corresponds to size of largest block and R2 corresponds to sum of sizes of Jordan blocks, and that also in this case is 2. So that means we will have one Jordan block of size 2. So what is the Jordan block of size 2? That will be a 2 cross 2 matrix as follows. So this is the Jordan block with eigenvalue lambda. Then let us look at lambda 1. So in this case, size of largest Jordan block is also equal to 2 because that is S1, and sum of sizes of Jordan blocks is equal to 4 because that is R1. So this means that we can write 4 as 2 plus 2 or as 2 plus 1 plus 1 because the largest size needs to be 2 and we need to add up to get 4. So how can we get 4 where one term is 2? We can get either by 2 plus 2 or 2 plus 1 plus 1. So these are the possible combinations. Now if we consider, let us say, the option 4 is equal to 2 plus 2, then the Jordan canonical forms, sorry, the Jordan blocks that we will use will be 3103 and 3103 because eigenvalue lambda 1 is 3. And if we use 4 is 2 plus 1 plus 1, then what we can get is we will get 3103 as one block, and then we will get just the number 3 as one block and 3 as another block. So that is how we will get. So that means, what are the options for Jordan canonical forms? So possible Jordan canonical forms, we can have two possible Jordan canonical forms, and they will be as follows. So first would be 3103, then 3103. This case we are looking at. And then for 9, it is 9109, just one Jordan block. Either this, or we can consider this option. So that is 3103, then 3, 3, and 9109. Again, the elements that I have not written, so it's 6 cross 6, are supposed to be 0. You can fill in the zeros for yourself. So these are the two possible Jordan canonical forms. So if we look at our options, so in this case, option number A would be the correct one. So option A is correct. This is using the following Jordan blocks. It is using 3103, this, and this. So this is that 4 equal to 2 plus 2 combination that is being used in this option. Finally, next we have some 2-3 simple questions. Which of the following statements is not true? So we have a bunch of statements about square matrices and Jordan canonical forms. So if in JCF of a square matrix A, there are maximum k consecutive ones on the super diagonal places corresponding to an eigenvalue lambda, then in minimal polynomial, the power of x minus lambda is k plus 1. This is a true statement. Why? Because any Jordan block would be corresponding to the eigenvalue lambda. What we have is, we have lambda, lambda, lambda on the main diagonal. We have 0, 0, 0 elsewhere. Then we have 1 and 1 on the super diagonal. So what is the super diagonal? Super diagonal is the diagonal just above the main diagonal. So you see that if it is a 3 cross 3 matrix, this is just an example, 3 cross 3. So we have two ones, and you can see that lambda occurs 3 times. So the x minus lambda, the corresponding power of x minus lambda in the minimal polynomial will be 3, whereas you have 2 ones on the super diagonal. So it is 2 plus 1 is 3. So this you can see for one particular example, 3 cross 3, but in general for k, it will also be true. Then option number B. So a square matrix is diagonalizable if and only if the eigenvalues are distinct. Now this is a false statement. Why? Because if all eigenvalues of a square matrix are distinct, then definitely the matrix is indeed diagonalizable, but the converse is not true. Why? Because you can have a case in which you have eigenvalues which are repeated, but if those repeated eigenvalues give you, suppose we have one eigenvalue which is repeated twice, so the eigenvalues are not distinct. The eigenvalue would be repeated twice. But if that eigenvalue has a geometric multiplicity of 2, That is, it is repeated 2 times, but it also gives you 2 linearly independent eigenvectors, then you can definitely diagonalize the matrix. So distinct eigenvalues would always give you linearly independent eigenvectors, but even non-distinct eigenvalues can also give you linearly independent eigenvectors. And if and only if, so this statement if and only if that is there, so if and only if is something which should work both ways. So that means a statement, whenever you have if and only if in a statement, that means the left hand side implies the right hand side, and the right hand side also implies the left hand side, which is not the case over here. In our case, eigenvalues being distinct implies that the matrix is diagonalizable, but that doesn't mean that a matrix will be diagonalizable only if your eigenvalues are distinct. You can diagonalize even with same eigenvalues. So that's a false statement. And the other two statements are basically true. The Jordan canonical form of a square matrix is not always unique up to reordering. We saw it in this example over here. We see that these two Jordan canonical forms are different from each other. They are not just different by reordering, they are indeed different because of these terms over here. And the roots of minimal and characteristic polynomials are same. This is true because minimal polynomial is similar to the characteristic polynomial, only its degree is lesser than the characteristic polynomial, but the roots will be the same. Then we have two questions on the accuracy of a classification. So we had a lecture, the very first lecture in this week was on classification matrix. So it tells you about the accuracy of your classifier. So the first question in this is, let sum of the classification matrix of a classifier on a data be given as follows. So this is similar to the example that was given in the lecture about being positive, negative. So true positive cases are 30, false positive cases are 30. That means falsely my classifier is characterizing them as positive even though they are not positive. Then true negative is 930 and false negative is 10. So false negative means those elements are not negative, but my classifier is falsely identifying them as negative. And true negative means they are indeed negative and my classifier is able to identify them as negative. Then we need to find out the precision. So formula for precision is as follows. It is true positive over true positive plus false positive. So this is 30 over 30 plus 30, that's equal to 1 over 2. So correct option is C. Next question, we have the same data as the previous question, but in this we need to find out the F1 score. Now before finding out the F1 score, we need to find out what is called recall. Now recall is basically true positive over true positive plus false negative. So this is 30 over 30 plus 10, that's 3 over 4. And F1 score is then 2 into precision into recall over precision plus recall. So precision we found out in this previous question, that's half. So 2 into precision, that's 1/4, times recall, that's 3/4, divided by precision, that's 1/2 plus, sorry, not 1/4, 1 by 2 I wrote wrong. 1 by 2 plus 3 by 4. So 2 and 2 cancel. That gives me 3 over 4 divided by, so this would be 5 over 4. So that's 3 over 5. So correct option is D. So this precision, recall and F1 score, so these are basically classify how good or bad your classifier is. So these are like accuracy measures of your classifier. So that's all for this assignment, and hopefully you can solve week 6 assignment of the current session based on these problems. So that's all for this lecture. So yeah, thank you, and that's all from my side. Yeah, thanks a lot.